All right, guys, welcome to our very last video of Unit 1. Tomorrow we're going to be doing an in-class lecture, so this is the last of your online lectures for this unit. To begin this unit, lesson, my prompting question for you is, what do you think of when you hear the word radioactive or radioactivity? Okay, you might think of this symbol right here, kind of a nice little warning sign being like, oops, stay away, right? You might think of like this green glowing goo, okay? Or you might think of this guy right here, the best Avenger, Mr. Hulk, okay? Who became the Hulk due to gamma radiation, which is a type of radioactivity. All right, so today what we are going to do is we are going to start looking into the last type of a nuclear reaction, which is radioactive decay. Okay, our objectives for today is that you can describe alpha, beta, and gamma particles and their penetrating abilities. You can use nuclear notation for radioactive particles. You can balance nuclear equations and solve for unknowns. Okay, and so our final question for our video lectures is, what is radioactive decay? To review, okay, there are three types of nuclear reactions. There's fission, there's fusion, and there's nuclear decay. We have talked about fission and fusion already. So by process of elimination, today's video is going to be about nuclear decay. Okay. I apologize that there are a lot of words on the screen right now. However, lucky for you, you can pause the video and copy it down. Okay. So nuclear decay can also be called radioactive decay or natural decay. And the formal definition for all three of these, because they mean the same thing, is that it is the process by which a nucleus of an unstable atom loses energy, okay, so I'm losing and giving off energy, by emitting ionizing radiation. Okay, very formal words. We're going to break it down to have it make sense, okay? And this occurs when a nuclei of an unstable, heavy atom breaks apart spontaneously. So it just happens. Nothing needs to hit the nuclei. It just happens. And when this breaking apart occurs, it gives off, or it emits, three types of particles. Okay? We got an alpha particle, a beta particle, and a gamma ray. And we're going to look at what each individual looks like. Okay. Elements that undergo nuclear decay are called radioactive or hot. Okay, so only nuclear decay gives off radioactive elements. We have naturally occurring radioactive isotopes called radioisotopes. Okay, those are potassium-40, carbon-14, and uranium-235. Okay. And the rate of decay is measured using a half-life. We're going to look at half-life tomorrow in an in-person lecture, but know that nuclear decay can be measured in half-life. This is what, sorry, that thing just popped up. I hit the space bar by accident. This is what radioactivity can look like, right? I have a heavy, unstable element. Okay, and it spontaneously decays, and I can form an alpha particle over here. I can form some gamma rays, or I can form a beta particle on top of protons and neutrons. Okay. So before we begin looking at the different types of particles, we need to understand what unstable means. Okay. Unstable means that I either have too many neutrons or not enough of them. Okay. My neutron to proton ratio is not there, okay? I am no longer stable. It becomes shaky. It wants to get rid of stuff, okay? And because of that, it's going to spontaneously emit, meaning release, different particles to become another element and become stable, okay? This is what radioactive is, okay? As we said, we have three different types of radioactive decay particles, okay? Pause the video right now, copy this stuff down, and then we're going to talk about it. All right, so an alpha particle. We can see it represented by its Greek letter here. So this is the lowercase alpha, okay? When writing it in a nuclear reaction equation, I can write it two separate ways. I can either do the nuclear notation for helium, right? 2 protons, mass number of 4. Or I can write it the same way over here, right? 4 mass number, 2 protons as my atomic number, and just put that Greek letter in there, meaning it's an alpha particle. All alpha particles are the same, sorry about that, are the same as a helium nucleus, right? There's no electrons in an alpha particle, but I contain 2 protons and I contain 2 neutrons, okay? So helium has 2 protons and 2 neutrons, which means, right, that an alpha particle is the same thing as a helium nucleus, okay? And if I were to weigh it out and compare it to the other types of radioactive decay particles, it's going to be extremely heavy, okay? It has a charge of +2 because I have 2 protons, right? Protons are positive, so I have a positive, and I have 2, so 2 protons plus 2 charge. It does not pose too much of a level of danger, okay? If I were to throw an alpha particle at you, your skin would be able to stop it from seeping into your body. And that is because I am extremely big and it doesn't move very fast. It's very slow. When it undergoes radioactive decay, my element that I start with is going to decrease by 4 for the mass number, and my atomic number is going to decrease by 2. All right, let's move on to the beta particle. Beta particle can be shown by this Greek letter here. This is the uppercase beta, the B, right? I can show it like this, okay? The E means electron, okay? I know electrons have a negative charge, and I'm going to give off 1 electron, so it's a -1. And I know that electrons have nothing to do with mass number, so my mass number is 0. I can also substitute the E for my uppercase B for beta. They mean the same thing. And a beta particle is made up of a high-speed electron, hence why I have that -1 charge here, and it's an E, okay? In comparison to the other type of particles, I am light, okay, because we know that electrons do not have a lot of mass. And because it is an electron, I know it has a negative charge, and it will be a -1 charge here. My level of danger is kind of in the middle. It's a medium level. And if I were to throw a beta particle at you, it would be able to be stopped by paper or a light metal such as aluminum, okay? The reason why it's going to be able to penetrate a little bit faster, or thicker, I should say, is that it is smaller and it moves faster, okay? In terms of a nucleus, okay, my beta particle is going to convert a proton, or my apologies, it's going to convert a neutron into a proton, okay, and my atomic number is going to increase by 1. Okay, so my mass number stays the same. My atomic number increases by 1. My last type of particle is my gamma particle, right, which shown as a lowercase gamma, which looks like a Y. Okay, gamma particles have neither an atomic number or a mass number, so no protons, no neutrons, and also they don't even have electrons. Okay, it is because I am a high energy photon, and photon is light energy. Okay, because there is no proton, neutron, or electron, I do not have a mass, so my mass is 0. Because I don't have any subatomic particles, I am also at a charge of 0. And gamma particles have the highest level of danger. It can only be stopped by a heavy metal such as lead. And the reason why, it is pure energy. Okay, it travels at the speed of light, which is extremely, extremely, extremely fast. Okay, its effect on the nucleus is there is no change. Okay, so my mass number, my number of protons, my number of neutrons, my number of electrons does not change. Or I shouldn't say electrons because they are not in the nucleus, but my protons and my neutrons stay the same. All right. When I'm comparing my penetrating ability, this is why I'm going to look here, right? Alpha particles here are not going to be able to get past my paper, okay? It's stopped because it's heavy, it's going slow, so it's going to be able to be stopped by something really thin. My beta particle here can go through this paper a little bit. It's going to be stopped by something thicker, okay? It's going to be stopped by the wood here, okay? My gamma particle here can go through everything. It can only be stopped by something like concrete or lead, okay? And it's comparing it all to a neutron, which continues to go through, right? So in terms of penetrating ability, gamma can penetrate the most, and because of that, it is extremely dangerous, okay? That's why if you have ever gone to the dentist and have to get x-rays, you have to wear this apron here, okay? This is to prevent the gamma particles of the x-rays from getting into your body, right? We don't want to harm you, so that is why you have to wear this vest. It's because radioactive decay is going on, and we do not want to harm you. All right, what I'm going to do right now, because we have a decent amount of slides left and I want to make sure I can get it all in, I am going to stop this video here and I'm going to upload part 2 of this video on YouTube. So please, please, please make sure that you continue to watch part 2.